Last lesson on solubility equilibria today. We don't have much to finish up after the very extensive do now. Hopefully you feel better about writing KSP expressions, solving them for molar solubility when no concentration is given, solving for solubility when you throw a common ion in, solving for equilibrium concentrations. All critically important. What I've seen on most recent AP exams is more of the first three types I gave you. And again, tremendous number of problems to solve in your textbook. Keep in mind, not only are the answers in the book for many of them, all the work is shown on Edline. It's very good practice. I highly recommend. This will be the last day that we look at Big Idea 6, where we'll really be exploring how external perturbations affect equilibrium. In this case, we're looking at equilibrium of solubility type expressions. So we want to look at what increases or decreases molar solubility. You've seen a little bit of it already. Where we're going to pick up, and there's a tremendous amount that has been axed out of this chapter, so I'll make it clear. I kept it in your notes. It's good to have for college. We finished off last time with calculating equilibrium concentrations of ions, and one of the do now problems explored that. So hopefully you do feel more confident with that type of calculation. I think that would be extensive. I don't think you'll see it, but in case you do, you'll be able to do it. What we were talking about in this section, and this is a big section, is we were looking at whether precipitation will occur. When does precipitation occur? When what is less than what, or when what is greater than what? When QIP is greater than KSP, and be consistent there. Put the Q first, put the KSP second. When QIP is greater than KSP, equilibrium shifts in the reverse direction, thus precipitation. We considered the steps that we followed. We wanted to look at how dilution affects precipitation, and then we calculated equilibrium concentration. You can determine whether precipitation is complete. You're no longer required to do this. One of the Pogel packets goes into a little bit more with selective precipitation, and we'll be taking a look at that. But we're going to omit all of this, and it was a little bit challenging. We're going to focus on selective precipitation. This is when you precipitate one ion and not the other. Now I wrote partially omit here. Some of it is still asked. Just the first part, which is the easiest part. When it gets very convoluted, that you don't need to know, so we're going to keep it really simple. With selective precipitation, you want to precipitate one ion, not the other. The example may read something like this. In aqueous solution that is 2 molar silver nitrate. Is that water soluble?
Yeah.
Yes, all nitrate containing compounds are water soluble. Is slowly added from a burette, and you'll see that slowly added wording, to an aqueous solution that contains 2 ions, both of which have a concentration of 0.0100 molar. You have chloride ion and iodide ion. Now, even if you didn't know that silver chloride and silver iodide are insoluble or barely soluble substances, how would you know from the silver nitrate what ion you were going after?
Nitrate.
All nitrate. Any compound containing nitrate ion is water soluble, so you're not considering the nitrate ion. That's the spectator ion. So with the silver ion. Now, these expressions may be given. The KSPs have to be given. You've got these pieces. Here's your question. This could be asked. Which ion, chloride ion or iodide ion, will precipitate from solution? We know that precipitation occurs when the solution has just been saturated, when QIP is equal to KSP. Here's your approach. You're going to solve for the common ion, which in this case is silver ion. Wherever silver ion has a smaller value or quantity, that's the first ion to precipitate. So if silver ion is smaller with silver chloride, then the chloride ion precipitates first. If silver ion has a smaller quantity with the iodide ion, then the iodide ion is going to be the one. When you are saturated, QIP and KSP are equal. So you're going to solve for silver ion concentration. You can use the KSP instead of the QIP for the reason we just discussed. Here's your KSP for silver chloride in blue up there. You're solving for the common ion. The chloride ion concentration was given. This you can do without a calculator. This is 1 times 10 to the negative 2. Negative 10 minus negative 2 is 10 to the negative 8. So that's the concentration for silver ion from silver chloride. You're going to do the same thing for the silver ion from silver iodide. You're plugging in the same concentration because they were the same. So clearly you can see that the concentration of silver ion is less than the concentration of silver ion from silver chloride. That means that silver iodide precipitates first because this concentration is less than this. So when concentration reaches that, silver iodide starts to precipitate. Okay? You can't calculate the remaining concentration of the first. Don't think they're going to ask you to do this. We'll skip it. They don't ask if the separation is feasible anymore. Just going to skip. I'm going to change my mind on B. I'm going to show you B. I'm not going to ask you B, but you'll have been shown. It says when the second ion begins to precipitate, you know that's the second ion because we established that iodide ion precipitates out as silver iodide first. What's the remaining concentration of the first? When chloride ion begins to precipitate, we establish that the silver ion concentration is this. You use that silver ion concentration in the KSP expression for silver iodide. So this comes from the chloride, and then you could calculate the iodide ion. Don't think they'll ask you it. I think we'll let it go. This problem is from the textbook. I'm going to change it slightly to make it easier for you. It says a solution contains 0.25 molar nickel 2 nitrate and 0.25 molar copper 2 nitrate. When sodium carbonate is added slowly, which ion precipitates first? Let's take a look. I'm going to work it just like we worked the previous one. Get the information down. We've got nickel 2 nitrate, .25 molar, copper 2 nitrate, same. We're going to add sodium carbonate. How do you know sodium carbonate is water soluble? All compounds that contain a group 1 ion are water soluble. You got it. And we want to know which ion precipitates first. What ions are we deciding between? Nickel, 2, and? Okay. KSP on this side is 1.4 times 10 to the negative 7th. KSP on this side is 2.5 times 10 to the negative 10. What do we do? Okay.
Divide each by the concentration of the cation.
So what are you solving for?
The concentration of
So now what do you do?
compare them to see which one is smaller.
So what's smaller?
The ones that
So which ion precipitates out first?
copper.
Mm-hmm. And truthfully, you didn't have to do all the math. How did you know that would automatically be it? In this case, because they're both S squared, but more than that, because the concentrations were the same here, and that KSP expression is both essentially S squared, once it has the smaller KSP, it's going to have the smaller concentration of carbonate on.
That really weird. Why did you put in carbonate? Oh, I didn't see the carbonated. Okay.
Because that's what we have. So that's what precipitates. All right? Not bad. Last piece of the puzzle is something you've already seen. It sounds really confusing. The only difference here is we're applying it to molar solubility, but you've already seen it with equilibrium and acid-base equilibrium. It says the solubility of an ionic solute is greatly affected by pH if an acid-base reaction also occurs as the solute dissolves. Before we even go into the notes, let's keep it really simple. Let's say that you have calcium fluoride, a barely soluble substance, as such. I want you to add hydrochloric acid, a strong acid. So we're going to add hydrochloric acid. Most chloride ion containing substances are water soluble. There are very few that aren't. We've looked at them. Silver chloride, lead 2 chloride, mercury 1 chloride. So most chloride ion containing substances are water soluble. So Chase, what do you think is going to happen?
Calcium chloride is going to be dissolved, and then it's going to form hydrochloric acid.
No.
You're adding the hydrochloric, so would you put that on the reactant side?
You're just throwing it in. Poof.
Oh, so then.
It's not on one side or the other.
Okay, so then it would ionize
Yes.
into H plus and the chloride ion, and then would it become hydro? No, no. would it
Yes,
become
yes, yes,
calcium
say it.
chloride and hydrofluoric acid?
Hydrofluoride. Well, you said calcium chloride.
And hydrofluoric acid.
Okay. So what is
And
the...
I said the calcium chloride would like dissolve because it's water soluble.
Okay. And then what?
So you don't need to go in with hydrochloric acid, is what I'm saying.
And then what? All right, so hang on. You are correct. I thought you went back to hydrochloric, but I may have misheard. So you're going to make hydrofluoric acid. Is that a strong acid?
No.
No. So you're going to get hydrofluoric acid.
And then would that increase molar solubility?
Yeah, wouldn't that increase?
Yes, it would.
Because you're decreasing.
Is that what you said?
Yeah.
You're brilliant.
Thanks.
I'm sorry, I misheard. I thought you went back to hydrochloric. So I either misheard or it was misstated.
Because
You're taking away the ion.
Exactly, you are correct.
Decreasing the concentration.
So by making hydrofluoric acid, you are effectively decreasing the amount of fluoride ion, and equilibrium will shift in the forward direction, thus increasing molar solubility. You like it, huh?
I like how the dotted line she drew symbolize the hydrogen on the fluoride ion is now
All right.
there.
But
So,
wouldn't it also decrease the concentration of the calcium 2 plus ion because it reacts with chlorine?
no, because it's water soluble. So it just, and that's where I thought he was going, and that's when I cut. I thought I thought you were relying much more on the calcium chloride. We'll go back and listen. Probably had it right. All right.
So like if we wrote on like a test that it was due to the decrease in concentration of both ions, would that be wrong?
Yeah, it would actually.
So
I probably wouldn't hit you on it, but it would. And I don't mean hit, I mean deduct points. All right, so the proton reacts with fluoride ion, generating hydrofluoric acid, which is a weak acid. Concentration of fluoride ion is decreased, causing equilibrium to shift in the forward direction. To replace fluoride ion lost, thus increasing, looks like a nice run-on, molar solubility.
Looks like you tried to write the green.
You put increase with a Q.
No, I didn't. That's just a sloppy G.
Wait, why
I'm a
did
good
that-
speller.
Oh, okay. It's upping.
You're a good speller as you write suppressing.
Yeah.
I spell things too.
Mm-hmm. I won my spelling bee. As a fifth grader, I beat all the sixth graders.
We didn't have a spelling.
Once upon a time, you used to have to know how to spell. Now they invented spell check. All right. Clear? There's other types of situations you can find this. And see the way it's written in your notes? Guys, let's refocus. I'm sorry I mentioned the spelling bee. My fault. Come on, come on, come on. Children. It's written a little more convoluted here, but you can see it well. I think you may understand it better the way we did it, because we kept it simple. Couple points I definitely want to make. Some salts are independent of pH changes, because if you had silver chloride, for example, if you had silver chloride, and you threw in hydrochloric acid,
Wouldn't that just convey more, yeah.
well, you'd be adding chloride ion here, you'd have chloride here, you wouldn't have that, and the HCl, it wouldn't go anywhere, so there's no effect on molar solubility there. However, it does say, and typically what you're looking for, the general rule is the anion is an effective base. The salt will show increased solubility. Examples of common ions include hydroxide ion, sulfide ion, carbonate ion, oxalate ion, and chromate ion, although the most common ones I think you would see would be hydroxide ion, sulfide, carbonate. Let's take a look at that.
Okay.
Yep.
Does MX mean salt?
Yep.
We're gonna need to know that?
Nope.
Okay.
It's just like metallic cation and X from the anion. You already do know it, but you may not be putting the pieces together.
Okay.
So for example, let's take a look. Let's say you had, I was going to do a hydroxide first, but we can look at lead carbonate too. So lead 2 carbonate, and let's do let's say you had this. What am I missing? Good. Okay, so let's say that you threw in strong acid, such as hydrochloric acid. Why does molar solubility increase?
Because the proton combines with hydroxide, which would form water, which would decrease the concentration of hydroxide.
Resulting in an equilibrium shift in the,
Or
to replace the,
lost hydroxide.
and as a result, molar solubility. You got it. All right?
Wait, sorry, I just,
You didn't like my back and forth?
no, you're just going, you guys are going really fast.
All right.
I missed
Let's go. We can do it. Add strong acid. The proton from the strong acid reacts with the hydroxide ion, generating water. Due to the decrease in hydroxide ion, equilibrium will shift in the forward direction to replace the hydroxide ion lost. With the forward equilibrium shift, molar solubility increases. More of this will solubilize. And you'll do the next one.
Wait, that's solubilize?
Yeah, that's what I'm-
Solubilize.
Why, like, wouldn't adding anything then cause a forward shift? Yeah, so, right.
What do you mean anything? If you threw hydroxide ion in, if you threw a strong base in, be careful. Well, that actually would be a mess because you'd increase this shifting, but it also would pull this out. That would be a mess.
What if you throw weak acid in? Would it still shift the forward just less?
Much less because you have such little ionization.
So usually I'm gonna ask you something that decreases the concentration.
Not always.
What else could there be?
If I said you added,
It could say like what should cause more precipitate.
yep, add sodium hydroxide.
Increase the concentration of hydroxide ion shifting in the reverse direction.
Yeah, well, this one also makes this, so that would be a big mess, but yeah. And let's say you had this. This one's going to be a little harder for you. What happens when you add strong acid?
Combines with the ion.
Now be careful, what does that make?
Carbonic acid.
It does make carbonic acid, and what does that decompose to?
Carbon dioxide and water.
Good. So you're effectively decreasing this, right? And so equilibrium will shift in the forward direction to replace the carbonate ion lost. And Andrew, what happens to molar solubility?
It increases.
Due to the forward shift. Yes, yes, yes.
So
All
when
right.
it shifts
If
forward,
they
it's
asked you
less
to write-
precipitate, so it's more soluble.
Correct.
If they asked you to write like a new, like which product was formed when you added strong acid, would you write water and carbon dioxide?
And that goes back to chapter 4, our favorite.
Why is it H2CO3?
You'd have a lot of proton in there, but it's not incorrect to say that you initially generated this. Regardless, you'll get that. It depends on concentrations and stuff. And it does say one practical result of increased solubility of carbonates in acid is the formation of huge limestone caves. And there's an interesting article in your textbook. Good read for you. Have fun. All right. You can link the math to molar solubility. For example, it says, what's the molar solubility of iron 2 hydroxide in a buffer with a pH of 6.50? You've got this, and you've got KSP. So it doesn't look like they're giving you much information, but from that pH, what can you ultimately get? POH and then hydroxide ion concentration. So you've already got this piece. And why is molar solubility equal to the iron 2 ion concentration?
1 to 1.
That's a power bond.
Mm-hmm. Alrighty? Because the power of 1 on iron 2 plus. Yes, yes? Alright, so you could easily solve that. This one, let's take a look at this. I'm going to diagram it out for you. It says, without doing detailed calcs, determine in which of the following solutions magnesium hydroxide is most soluble. You've got magnesium hydroxide. I know, sloppy floppy. Do we want to
COH close parentheses 2.
Let's write it again. Just for you. Since I may have told you no when it was a yes, I'll eat it. I'm just teasing. I adore having all of my kids in class, and everybody's here today to play with me. Come on, Faith, let's focus. Okay. If we're trying to figure out which causes increased solubility of the magnesium hydroxide, we will need a solubility equation, correct? Makes it easier. What's your answer and why? You do need two O's. How come?
Because there's balance and hope.
Just seeing if you're awake. What do you got?
No, I just have a question. Why did you write NH4CO? This is what I started.
Yep. But I'll write it if you want me to. Yep.
1 molar ammonium ion.
Why?
Because ammonium combines with hydroxide ion. Ammonium hydroxide decreases the concentration of hydroxide ion, shifting the reaction in the forward direction, increasing molar solubility.
Hang on.
Great.
Hang on, hang on.
No, I got that.
Hang on.
Good for you.
No, I was trying to.
Does this stay as is?
No, it goes to ammonia and water.
And that's the key.
Can you just always add another H to make water? Oh, just kidding. There's not. Just
Okay. All right. So these two react, forming this,
I thought you said ammonium.
which rapidly decomposes to ammonia and water. This is back from chapter 4.
I remember that.
Effectively decreasing concentration of hydroxide ion. With the decrease in concentration of hydroxide ion, equilibrium shifts in the forward direction, thus increasing molar solubility.
Good thing we'll watch after this.
Name a strong acid that would have the same effect. That would. Any strong acid.
Sulfuric acid.
I was like, it's all of them.
You get sulfur dioxide.
So,
Right.
so with all of those, it would. Wait.
But what if
No, it's this one we decided. This is the best answer. That's the next best
The
answer.
second one would only partially work, and then the first one.
That's a bomb.
So that one's the best answer because when it dissolves in water, okay, cool. But when what does the second one do?
The second one could as well, because you do have some of this in here, but you have a lot of buffer solution here.
Wait, so those two are together?
This is choice A,
No, I know
B,
that. No, I know
C.
that. But like B is you're adding both of those.
Correct.
So the better answer is to have one singular ion than two.
then a buffer solution.
Yes. Okay.
And what strong acid would work?
Anything that forms anything.
Well, that's specific.
All right, this whole complex ion stuff, gone. And honestly, I don't think they could do a tremendous amount with this either, because this requires extensive knowledge of solubility rules. So I don't really foresee you having to do that type of analysis. What you want to make sure you can do, those do now problems we did at the beginning, the smidgy on selective precipitation, and understanding that pH can affect molar solubility. I want to say one more thing because I didn't link it in and I can do it right here. I always said For example, with this one, we were adding strong acid. Why would decreasing the pH also increase molar solubility?
Because it makes it more acidic, so would it cancel out the hydroxide?
It makes it more acidic, so you have more of what?
The
Protons. So at lower pH, the concentration of proton increases. Those protons react with the hydroxide ion. So you generate more water. So you have more protons. So you can either add strong acid, or in your notes you may want to go back and say decrease pH, because you could state it either way. I just want to make sure it's clear. Now if you add NaOH, you also could increase pH. You'd have more hydroxide ion, thus causing a reverse shift in equilibrium, which would do what to molar solubility? Decrease it. I think you've got it. Question?
What if the reaction isn't acidic or basic design?
Well, then equilibrium will have been established, and if you want to further affect molar solubility, you'll do something else. And keep in mind, very often equilibrium is established, and then you perturb the system in some way, and that's the whole big idea 6.
Like when you're doing electrochem last year.
Now, I'll answer an electrochem question separately. At this point, that's the close of molar solubility. You want to make sure you do some practice problems in chapter 16. You already have your practice quiz, and you have both POGIL packets. If you go big, you will do well on Tuesday. If you open all of this up Monday night, I of course wish you good luck, but you make me nervous when you do that. Okay? Put the time in and you'll get the results that you so desperately want.